In this presentation, we're going to look at the chi-squared goodness of fit test, and we're going to use it for a Poisson distribution, okay? And to see if a data set is correctly modeled as a Poisson distribution. A factory manager wishes to know whether or not the number of rejects produced by an industrial process within a set period follows a Poisson distribution. So this is an important little phrase here, within a set period. So let's just say this is a 4-hour shift or something like that, okay? It's sort of hidden a little bit, actually. It's deliberately hidden a little bit. So this is actually related to the definition of what a Poisson distribution is about. The modeling the number of occurrences in a set time period or a set unit space. In most cases, it's time periods. Could also be volumes or areas. Okay, and each experiment, so to speak, or each shift is independent from the other, but the parameters, the probabilities, will stay the same. Like, for example, in this case, it is 1.5 rejects would be expected in each shift, that sort of thing. Okay, so the previous month's data given below are thought to be typical. So this is the number of rejects and the number of shifts where that reject or that number of rejects was the number of rejects. Okay, so for example, there was 38 shifts, okay, where there was 0 rejects, or there was 49 shifts where there was 1 reject, 43 shifts where there was 2 rejects in each shift, and so on, 17, 3, and so on. So for what reasons might the rejects follow a Poisson distribution? Well, essentially I just sort of covered it over there, part A. Okay, now this is anything that sort of describes, knowing what the definition of a Poisson distribution is about and the theory behind it and so on, just sort of show how this is sort of would be relevant in this situation. So if the process is producing individual rejects at random and at unpredictable instances of time, but at a constant rate over the period of study, then the number of rejects during a fixed time of observation will follow a Poisson distribution. That's the sort of textbook definition, but essentially something along those lines. Okay. Okay, so what we're going to do here is test a hypothesis that the distribution of rejects is Poisson, okay, and explain your results to factory manager, okay. So yeah, again, just actually state what the null hypothesis is that the occurrences of rejects follows a Poisson distribution, okay. Now, what we have to do here first off is calculate the mean number of rejects per shift, okay. So first off, what we have to do here is calculate how many shifts there are altogether, and it turns out that there is 160, okay? And what we have to do then is find out, in that 160 shifts, how many rejects were there altogether, and it turns out there was 240. So there was 38 instances where there was no rejects, so no rejects. There was 49 instances where there was 1 reject. Okay, so that's 49 from that bunch. There was 43 shifts where there was 2 rejects, so that's 86 for that, and so on. So essentially, there was 240 rejects altogether. Okay, now this is a good bit of number crunching there. So you just have to figure out that overall that there was 1.5 rejects per shift on average. Okay. So the mean is 1.5 rejects per shift. Now, actually, it doesn't say shift there. I'm using that phrase myself, so I'll just say unit period. 1.5 on average. Okay? So, that's important. Now, what we're going to do here is calculate the expected number of rejects in each shift, okay? Now, in this particular instance, what I'm going to do here is I'm going to sort of be very brief on this part here, okay? So essentially what we do is we're going to calculate the probabilities for each of these, or for each of these number of rejects, okay? up to 4, and what we can do is we can treat greater than 5 separately. Okay. So the expected number of rejects per shift following the assumption of a normal distribution will be the probability times 160. Okay, so if you work that out for R is equal to 0, like what's the expected number of shifts where there will be no rejects? It should work out to be 160 times 0.375, something like that. Okay, and that gives us 35.7 is the number of shifts we expect there to be no rejects. Likewise, R is equal to 1, calculate the probability, works out to be, I don't know what it is, I'm not going to do it off the top of my head, but essentially 45% or something like that. But anyway, it's a sort of we expect there to be 53.55 shifts where there is exactly 1 reject, and so on, 40.6, 20.08, 7.53. There's actually, I've actually sort of skipped over a bit of work here, but there is actually quite a bit of number crunching involved in this one. Okay. Now, just as a remark, for the probability of greater than equal to 5, essentially just add up all of these here, and it should work out to be 157.02, and then just get the difference there to add it up, so that it adds up to 160 overall. That'd be perfectly fine. Essentially what you're doing there is it's just rounding error. So I'll just do that again. The sum of 35.7 all the way up to plus 5.73 should add up to 157.02, and that means that there must be 2.98 expected for greater than or equal to 5. Okay, and that should add up to 160. That's how you get that. Okay, so the difference there is 160. Is 2.98. Okay. Now, so yeah, that's how you get them there. Okay, so what we're going to do now, this is the important bit for this part here. Okay, this is the really important bit. Now, hopefully you should have seen chi-squared tests for independence of categorical variables. Now, this is a slightly different matter. Okay, when we're fitting, seeing if distributions fit, like the binomial, Poisson, and normal, what we have to know is these degrees of freedom here. Okay. Now, there's a little bit of theory there behind it, but we won't have to worry about that too much. It's not a theory exam, it's a practical question. So essentially what you have to know is just like binomial, or binomial, sorry about that, little typo there. Would it be n minus 1, Poisson would be n minus 2, and normal would be n minus 3. Okay? Now, so in this particular instance, what is n? N is the number of categories that we're dealing with. So it's essentially, we are dealing with 6 categories. N is equal to 6. So that means that the degrees of freedom is equal to 4. Okay. So a chi-squared test, that's a critical value. Now, we're not really told a significance level, so assume 5% until you're told otherwise. Okay. Could be different. So this is from 9.488. That's from the chi-squared critical value tables. Okay. Now I sort of skipped over that part, partly because you should have done should have been introduced to chi-squared tests already before you tackling this material. Okay. So just to sort of remark, 9.488, something like that, should be the chi-squared test. Okay, so now what we're going to do is calculate the test statistic, and this is the standard formula for calculating the chi-squared test statistic. So what we're going to do here is the observed minus the expected, square that, and then divide it by the expected value. Okay, now just to be clear, it is these values here. These are observed. We have 6 observed, 6 expected values there. Okay, So 38 and 35.7, 49 and 53.55. There we have them there. So it's a good bit of number crunch there. I've actually included it this time. So this is the test statistic here, test statistic, TS. So essentially what you just have to run through it there. And a good bit of calculator work. Give yourself 10 minutes and you should get a test statistic there of 3.13. Okay. So is the test statistic greater than the critical value? No, it's not significant. It's not significantly different from the expected Poisson expected values. So that means that there's no reason to reject the null hypothesis that the data follows a Poisson distribution. So essentially, what we can sort of say here is that, you know, the number of rejects per unit time period is expected to remain reasonably constant, and they do not arise in any regular or predictable way. Okay, so it's just random. Is in other words random. They are at random. Okay, there's a randomness about them. This would be sort of relevant to predictability is in industrial processes a different matter. So it's a random process, random Poisson process. Okay, and it should follow this pattern or a pattern close to this reasonably consistently. Okay, and if it does, nothing to worry about. Okay, or nothing unusual is going on. All right, we'll leave it there.